Welcome once again to the lecture number 17 of the deep learning course. In this session, we are going to talk about the computer vision. And this particular topic is very important because many of the technique that actually we actually develop with the help of deep learning, they are going to solve the computer vision problem. So earlier, what was happening that computer vision was very difficult to solve, and uh, the promises that this computer vision this deep learning has shown in the domain of computer vision has actually made it more popular. So essentially what I mean by this, that whatever things you these days you talk about the deep learning, they are mostly because their success into the computer vision domain. So let us try to understand that what is the computer vision and what are the basic part, and so that you can later, when we are going to discuss about the different architecture which actually solve this problem, you can appreciate that what are the how the things are actually done by your system. So let me start by giving you the basic introduction and the under assumptions that what is the computer vision. So from very high level perspective, you can think that you are actually training the systems to see something. So for example, here is an image. So what you see from here, if you can describe it, you are doing computer vision. So how can you describe this? Try to describe something. So you may tell that looks like that there is a plant where there is a leaf. Okay, you can tell that there looks like that there is a leaf. If you look closer, you can see that there is a grassy background over there. If you more closely look, you can see that looks like that there are few things which are actually cut. So look like that there is some problem. For example, you can see that this leaf has problem. Here is also leaf some problem. So why this particular problem is this? What kind of problem it could be? So if you very clearly see, I think it is very difficult to see earlier, but now you can see that there is some culprit is also available into this particular scene. So where is this particular part? If you see this image from very from a distance, it would be very difficult to anybody to come up with this kind of thing. So look, this is difficult for us. So for the computer, it is again going to be more difficult because we ultimately have to tell the computer that how to see all these things. Designing these systems is actually challenging, and this actually takes a lot of things into the account. So you cannot do this as an individual study. Many things are coming, for example, from the you have to apply artificial intelligence. Ultimately it is artificial intelligence. Automatic learning, you have to apply information retrieval, different kind of architecture you have to do, machine ML architecture you have to try. Algorithmic perspective means you want to make the things more fast, you have to apply graph. Some many things come from the graph understanding of the graph: cognitive science, neuroscience, optics, image processing, speech, NLP, robotics, physics, whatnot. So many things actually contribute to this particular domain. Then only you would be able to solve this particular problem efficiently. uh, Nowadays we have a lot of data. Earlier people actually were talking about that we have very less data, but now it is not the case. And now we have the number of camera on the earth is actually more than the number of peoples on the earth. 80% of the internet traffic is video, so a lot of training data is available. We want to make it successful. So this all started, computer vision started long back, and this is a very interesting piece of piece of advertisement that everybody want to everybody shows when he actually teaches this particular course, that in MIT around 1966 they thought that we can solve all the problem related to the computer vision in a summer time. Okay, it was a summer vision project. So this is an advertisement issued by the MIT, and they thought that how can we into the summertime, means into 2 or 3 month duration, how can we solve all these things, all the computer vision problem very effectively. So summer workers which are actually students who apply over there, they were trying to utilize this their effort, and they want to make all the system that can do the pattern recognition and all these things effectively. But we have seen that even after 50 years it was not, we are not able to do that effectively. So broadly, if you want to do a computer vision task, you have to do the classification. Means classify means multiple items are there. You can tell that here is a cat, here is a dog. You want to do the classification. You want to do the annotation. You want to write something about this. You want to do the detection. Where is a cat? You want to do the segmentation. Give me that particular part of the image where there is a cat. So all these things actually we want to do into the basically we want to do into the computer vision. So this is a very interesting actually article. You may have seen this this particular image earlier also. So there was a National Geographic photographer who have taken the image of this particular a girl who was I think 16 year at that particular time, and she was living into the refugee camp. And after some time, when this girl grew up and become old, she somehow caught into the Pakistan, and it was they were trying to establish that what is the identity of this particular girl. It was very difficult to find out at this particular problem for this particular girl, and she was stuck into the problem. And by chance, I don't know how, that the same person has again taken the image of this particular girl, and using the iris pattern, it was actually the connection was established that they are actually the same persons, and this particular problem was solved. So computer vision actually is this particular image actually got a very big media attention, and people were talking about this, that okay, they can solve this kind of very difficult problem, that matching whether this is the same person or not, it is very difficult, but using iris they can solve all these things. Nowadays, there are various methods available, and this is a very recent paper came out, I think, around 2018, where using GAN, they were actually generating generative adversarial network. They were actually generating fake images. I mean, the peoples who are not existing on the earth, but your system is automatically generating fake images. So let's assume that there are two images, and this is one image, this is another image. And if I say that one of them is, let me say it A, and then let me say it B, and if I ask you that which image looks to you that it is a fake image, and another is a real image, can you give me A and B? So if I use that particular system, then can we tell this thing? It is very difficult to tell. You are Mohit is telling it correctly. Actually, both are of these images are actually the fake images. Okay. So we can generate these images is very high quality of images, and it is very difficult to distinguish for the original from the original images. The problem of classification actually says that let's as we have discussed earlier, that problem of classification is this, that multiple things are there. For example, in some images there is a aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. So some images has been taken. So this is a database, very popular database called Cipher 10 database, and on this particular database 10 categories are there. Your objective would be that given a particular any specific image, for example, if I give you this image, you have to tell that it is dog. If I give you this image, can you tell me that there is a horse? Very interesting problem, and people actually solve on this thing, and they are getting good accuracy nowadays. So after that, Cipher 20 database has been introduced, and a lot more things people do. So this is the classification. On the given image, you want to attach a particular label on that to that particular thing. Classification is challenging because it may be possible that you are taking the things in a very different way. For example, here illumination variation. You can see that only because of the illumination, the lot of change into the, you can see that appearance drastic changes drastically. Here there is a monument, and for that, if somebody has taken the image and he is taking the image from the different directions, so different kind of image, you can see that there is there things which actually see may have the large scale variation. So and deformations and occlusions means some part is not visible. Occlusion, background clutter. Here if I give you this image, finding out where is the cat has become difficult. Looks like that the cat is here. I may also be wrong because the similar kind of background is there. Intra-class variation, which actually also is a big problem. If I want to find out whether there is a chair or not, chair could not be of the same type. So different kind of chairs can look totally different, but they are actually chairs. But what we can do? Annotations is another problem that we want to solve, and annotations means given the image, you actually want to tell something about these images. For example, here you want to come up with these, what are the important words, and then using those words you can come up with the story that is possible. So there is a paper which is actually reference over here, ECCV 2008 paper, and you can just see a new baseline for the image annotations that actually try to solve this particular problem, where human has told for this particular image as a sky, jet, plane, and smoke, and the system was able to tell a sky, jet, plane, smoke, and formation means very near to the thing. So now deep learning is very near to solving all these problems. Detection is another interesting problem that we have talked earlier, that you want to detect in an image. where is the item which to which I am actually interested in. So you can see that there are multiple papers which are actually addressing the same thing here. Person one is detected here, second is detected here. Again, the similar kind of problem come. For example, one people can be another can be occluding other person, and therefore occlusions and multiple peoples into the scene. All these challenges actually come into the picture. Description is another thing where given an image you want to describe that thing. So one idea is this, that you try to come up with different kind of boxes on the scene, and then for every respect to every box you actually apply, find out that what is the word over there, then you combine all these words and then come up with a story. So this is a paper, dense cap, fully convolutional localization network for the dense captioning. So Fifi Lee, who is the one of the very big researcher into this particular domain, CBPR 2016 paper. Then comes a very interesting problem that is called the segmentation. And the problem of segmentation is this, that given an image, you want to find out where is the thing for which I am interested. For example, in this image, sometime you would be interested that where is a road. Why? Because if you are developing autonomous driving vehicle, so the vehicle should know that where is the road and where is the lane. Okay, where is the lane markers, in which lane I am, what is written on this thing, what is the instruction written on these boards. So you have to find out that. Looks like one color represent one kind of item. So looks like that here is a road, here is a tree, you can see that here is a tree, so trees, here is a tree, and I think here are the shops, then there is a tree and there is a sky. All these things you have to find out. Very interesting problem is here, where in a hotel room you are going to tell that where is a bed, where is a wall, where are the photographs, and all other things you are going to tell about this particular image. Segmentation is very important problem, and many of the time you actually want to solve the segmentation problem at the different scales. For example, sometimes you want to tell that if this is you want to do the segmentation here. For example, this is an image for which you want to do the segmentation. Sometimes you want to tell that looks like that these are the boundaries. In one boundary there is one item, or you want to only fine grain to the particular item and tell that these are the boundaries of the item. Can you see that there are two different kind of problems? One where you are telling that in this particular area there is an item, in this particular area there is an item, and this is another kind of segmentation where I'm telling that I'm closely telling that only these are the items available. And the third class could be that for every item I'm going to also going to tell that this is type A, this is type B, this is type 3. Different kind of items actually I'm going to put in front of you. So all these things we want to do, all these things actually we have discussed that we want to do with this kind of data. But for the computer it's not easy. Why? Because computers see, whenever there is an image, computers see the number. For example, 30, 25, 18, 81, 32, 55, 91. So different kind of numbers are there. Okay, different kind of numbers are there. Computer is only seeing these numbers. By seeing this number, even you cannot tell that what is over there. If I plot them as an intensity, for example, here into the 3D view, so on the z-axis, what is the intensity has been shown. So if I plot that intensity, then only you would be able to see this kind of thing. Okay. So for the computer, it's not very going to be a straightforward thing, but from mathematical perspective, you can think that image is a kind of function. Image is a kind of function that actually that is going to be from r square to r. Means there is some r square means what? X y location. You are going to provide x y location, and by this it is going to give you what is the intensity at that particular place. So mathematically, you can represent the image using this particular notion, where you say that at every location it is going to be a array only, and every location there is some value, and this value actually going to tell you that what is the intensity at that particular place. All right, if you can do that, then different kind of operation is also possible. Mathematical operation that you actually apply. For example, this is very interesting application where you say that what if you take any value and you add 20 to that. Okay, you take some value into the image and you add 10 20 to that. What does it mean? You are increasing the intensity. So if this is an image, it becomes this image. Make sense? Do you agree with me that this is the another image where all the dark are going to be less dark, because now 20 has been added, fixed number has been added. However, you can see that however these two images are not same. These two images, are they same? No, they are different because every value is being added 20 this time. However, from the understanding perspective, if you go over here, then you would tell, okay, looks like that both of them are same. Understanding perspective, you can say that both of them are actually same. Here's another example where I'm going to apply a different kind of mathematical operation that say that f minus xy, and here I assume that you can very quickly understand that minus x means what? The counter position into the x direction. So if I pick any pixel over here, so counter x direction, maybe this particular location of that particular thing, it is minus x. I represent the minus x by this. I'm going to exchange them because y is going to be the same, x and minus x. If I change them, what is going to happen for every pixel? If I'm going to do this, so what is going to happen? This image become this image. This is the mirrored image of the same image. So this kind of simple mathematical operation, you can think that because being a number and being a vector, you can apply all these operation on the things. Any questions on that? Any questions on that? Till now, any confusion, any question? Yes or no?
No, sir.
Please type. No? Great. So I'm going to start this discussion using this kind of small representation that I wanted to tell you that let's assume that I'm going to apply a kind of, okay, what do I mean by point operation? That on one value you are going to apply something so that you get another value once again. So if I sub r to you, you are going to give me a value s. So instead of r, I am going to s. 1 minute. So if you have an image, you pick a particular pixel. What is the intensity over here? Let's assume that intensity is r. Can you see that? Okay, I think I'm freezed. So why it is like that? 1 minute. 1 minute. Okay. Anybody, can you tell me that I'm audible? Am I audible?
Yes, sir.
Am I
Yes, sir.
audible? Yes. Yes. Okay. 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 So all right. What I was telling, I think in between I was stuck. You may not have heard about this. So what I was telling that let's assume that there is some value r. I am going to apply a function on that, and then what do I mean by this? That in an image, what do I mean by this? In an image, if I pick a particular pixel and the value is r, what I'm telling that instead of r, I'm going to use m of r, which I'm going to say that it is s. So what happens that this image actually changes to something else. Okay, I wanted to understand that particular part. One image that is given to me, I am going to change that image and I'm going to get something different. So let's assume that on this side I'm going to tell that what are the intensities of that particular pixel are, and this side I'm going to tell that what is the s that I'm going to get. So this intensity, you can also say that let's say r values are here. So if I draw a line like this, so if you draw a line like this, so you know that intensity, once again, let me tell you that intensity can take the value from 0 to 255. 255 is the maximum value. Intensities can take the value from 0 to 255. 255 is the most brightest one, 0 is the most dark one. Make sense? If I draw the line, which actually is going to convert my things from one to another, this is the line. If m is this particular line, so what is going to be the image? If I have an image, I transform this using this thing, what is going to happen? No change, because it's a 45-degree line. So what would happen that if some value, if I have some value, for example 30, so if this value is also going to be the 30, 255, I'm going to get a 255. So same image I'm going to get. Are you okay? Yes or no? Same image I'm going to get. Yes. If I draw a line like this, if I draw a line like this, okay, what would happen? That actually this time what is going to happen? So if I pick this particular value, for example, if this is 200, 100, earlier I have to reach to this particular point, but now my point is this, so I would be getting this thing. So what would happen? That intensity, brighter things become dark. Now my image would become dark. So can you see this? My image would become dark. So what is the maximum value that I'm going to get? This. So earlier I was able to get the 255. Input and output both could have the value 255. But if I use this particular line, as a transformation function, then I would be getting this particular value only. So I am shifting the things. I am actually pushing the things toward where I'm pushing I'm pushing the light things, the things which are actually light towards the dark. Now the things would be more darker. Similarly, if I draw a line like this, similarly you can think that if I draw a line like this, okay. Similarly, if I draw a line like this, so this time what would happen? That these things here the value, earlier value was 50, instead of 50 now it becomes 100. Okay, now the things would be more brighter. So this is the concept. This is the simple concept that you can apply. So if you understand this particular part, you can appreciate this thing, that if I use this particular line means what? I am actually darkening the thing. Okay, because earlier the things were this, but now you can see that they are darkening. Lesser value I'm going to get. Are you okay with that? Yes or no? That this is going to be darkening? Yes or no? Similarly, this is lightning. You can see that earlier the value was this, but now you can see that instead of this I'm going to get this value, instead of this I'm going to get this value. So it is darkening. Compression towards the dark, compression towards the light, and this is the high contrast, low contrast. All these things are possible. Okay, so emphasize the shadow, emphasize the light. I suggest you that please you go and by yourself try to understand that what do I mean by all these things. Okay, you try to explore this particular concept by yourself and get the idea. Now I'm going to tell you another thing, something called the histogram. Okay, and what is the histogram? Histogram is a kind of probability distribution of the image intensity values. It is a probability distribution of the image intensity values. Okay, what do I mean by this? So let's assume that this is the image I have. So what is the pixel intensity at this particular location? I don't know. Maybe this value is 100. So right now it is a RGB image. So you can see that if R, G and B images are there, you can always divide and find out summation and divide by 3 to get something that is going to represent between 0 and 255. And this is the one way that you can convert the colored image to grayscale. So right now I'm talking about the grayscale image, and later onwards, whenever an image is there, our understanding would be that it is going to be a grayscale image. However, the better value, better percepted value is obtained when you apply some weight to these things, and then you divide these things. So we are not going to in that much detail. But again, understanding is this, that this is an image, and you find out a grayscale of equivalent, and you look a particular pixel location, and let's assume that particular value intensity at that particular value is 100. My question is how many pixels are there whose intensity is 100? So maybe here also you can find out some intention, some pixels where the intensity is 100. So you can say that 30 such pixels are there. So at the value where there is 100, I would put 30. I would put a line of 30. Similarly, how many things are there which have the intensity, for example, 150, these many, 151, this 42. So for every intensity value, I am going to count that how many pixels have that particular value. And if I make this kind of graph, this particular graph is a special kind of graph. It has a special kind of name. And what is that name? Histogram. For this image, I have created this histogram. Any questions, if you have, please let me know. It is very important concept. Hope you understand this. If you have any confusion, let me know. What is a histogram of an image? For every pixel intensity, I am going to find out that how many pixels have that intensity. If I plot like this, it is going to be this kind of graph, and this graph is called histogram. This plot is called histogram. Make sense? Yes or no? All right. So there is something very interesting idea that if you draw a histogram, you can by yourself think that if you have an image and you draw a histogram, so whether in every image you would find out something with the intensity 0. Maybe not, because some images are such that maybe these intensities are not available. Maybe these intensities are not available. Maybe only these intensities are available. It may be possible, na? Most of the thing this is going to happen. So if you plot the histogram could be like this. Are you okay with that? That you plot the histogram. The histogram could be like this. So here, if you just try to understand this particular kind of image, you can see that 0 values are not there. These human can perceive, but these values are not there. Human can perceive, but these values are not there. So it is not a good idea. Sometimes we say that using this area only, using this area only, you whatever pixel, for example, this pixel is for example 50, make it 0. This pixel intensity make it 0. If this value is for example 110, so 110 make 255. You take it 255. And similarly in between things also you can stretch, so you can draw something 0 to 255 line over here, and you stretch this thing from here to here. So what would happen? This particular thing would look like this particular task, this particular process is called the histogram equalization. How you do that? Once again, you have to apply some kind of mechanism to do the histogram equalization. You have to find out that how many pixels, how many things are there. Then you find out the cumulative summation, and then using cumulative summation you actually do the scaling, and then you get this kind of structure. And this kind of histogram is called the equalized histogram. This is the histogram. This is called the histogram equalization. Let me tell you very interesting ideas. Can you see this image, and do you understand that this is a good image? So looks like that. I don't know that what is the word there. So if you see the histogram of this particular image is this. If you apply a histogram equalization using this kind of curve, what you are going to get? You are going to get this kind of image. Is it a better image? Yes or no? Yes or no? And new histogram is going to be this. Make sense? Is it clear? Yes or no? Let me show you another image. So this is another image. I don't know that how much you can visualize out of this, but this is what the histogram of this particular image is. If you apply histogram equalization, you get this image. Surprisingly better image. And this is what the new histogram looks like. So I want to ask you a question, that if let's assume that this is an image and this is an image, there are two different images. If I draw the histogram, whether the histogram is going to be the same? Yes or no? If I give you two images, whether their histogram is going to be the same? Most likely not. Okay, most likely not. It is not going to be the same. Okay, so can I represent this image by using this histogram? And either can I represent this image using the histogram? Yes or no? Okay, as a feature I can utilize it. Okay, however, it looks like that this idea is not good, because let's assume that here is an image and you can see that who is he? He is zebra. If I randomly shuffle the image, for example, this place I put here and here I put here, randomly shuffle this image, what this image would become? This image would become this. Can you understand that there is any zebra here? I have shuffled it. But if I find out that what is the histogram of this particular image and this particular image, this particular image and this particular image, whether they are going to be the same or not, whether the histogram of both those images are going to be the same or not, they are going to be the same. But the images are not same. Similarly here, you can see that here is a panda, here is no panda. We have just done the random kind of permutation shuffling over here. Histogram is same, but the image is not same. So histogram cannot be utilized in that particular way. We need some more local parameter to describe the image, because if you want to describe, you want to find out the right kind of feature, we have to do something very interesting. So one more thing that we wanted to talk about with respect to the image processing, that if you have, for example, there is some elephant standing somewhere and you want to take the photograph. How many of you like my elephant? Okay, 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 okay. So it is a NFT. If you want to purchase, let me know. So let's assume that there is a lion somewhere is standing. I have actually deployed a camera, and I have taken this particular image of this particular camera, this particular lion, and I have created this particular image. You know that all the cameras that actually we use, they have something called noise. So if you take two images at the with very near time, so they appears the same. Both the images would appear the same, but the value. The pixel value, if you want to compare, there would be some noise. Are you able to see that? But there would be some noise. This is the fundamental property of anything, that when you actually acquire something from this system, there would be some noise. So how can you get rid of this noise? Because same thing, once again, you want to represent this image, and you have seen that in both the images there is a line, but the values are different. How can you think that how can you do some kind of processing that can make them similar? One such idea is that you can apply. For example, this is what you can see that if you on a particular pixel you are measuring that what is the value at that particular pixel. So it could be something like this. So sometimes it is this much, this much. So this is going to see that what is the intensity at that particular thing. So once again, I right slide. So let me wait. Let me wait. Yeah, I think now you are on the right side slide. Okay, what I was telling. So let's assume that on a pixel symbol on a pixel, you are actually wanted to find out that what is the intensity over there. So you could be getting this kind of intensities on a single pixel. Sometimes this much intensity, sometimes this much intensity. Why there is a variation? This could be variation because the scene is actually varying, but this looks like does not look very good because there is some other effect is also there, and that is the effect of noise. You understand, something is happening because of this, the things are changing, but there is something else is also getting impacted because looks like that it should go like this, but here these values are actually lesser. How can you get rid of that? So one basic idea is that you can apply the moving average, means you can take some of the location and you tell that for this particular region I'm going to put the average on this particular place. So instead of using the exact value, you are going to use the average into this particular place at this particular place. If you do like this, your things are going to be get smoothened, and you can see that this is a better representation of the signal as compared to the previous one. So you understand that what is the moving average, concept of moving average, yes or no? So if you understand this thing, you can also tell that sir, it may be possible that it is good to have all these things. For example, if I want to find out that what should be the value over here, I'm going to consider this area to this area. So why not you give more weightage what is value over here as compared to the previous thing? So this is also possible. You can apply a kind of weighting, and most probably you are want to apply a Gaussian kind of thing over there to find out that what is the value over there. Again, the weighted multiplication is also possible to find out that what is the actual value over here with respect to a small neighborhood on this. If you do these kind of thing, this is going to remove some kind of problems from your system, especially when there is any noise and other things. And this thing is called convolution. This kind of operation is called the convolution, and we represent this using this kind of function. So whatever earlier thing you are having, you actually multiplied with a kernel, and by this you are going to get something new. Okay, you have applied to this thing is called kernel. So what is the kernel? Once again, not very difficult thing. Some kind of weighted matrix that you are going to that you come up over here. So just see an example where I'm going to tell that let's assume that this is an image that you somehow computed. You somebody has given you this particular image. So in this particular image, what is? Can you get this kind of image? Can you see this? That it looks like that here is 0 means here is dark. Here is 90 means there is some window in this, and somebody has given me 90 over here, and somebody has given 0 over here. How is it possible? Generally it is not possible. Okay, looks like that. If it is 90, so here also there would be 90. If it is all these values are actually 0, so this value should also be 0. If you apply this kind of method that we had just talked about, means if you apply average of this particular quantity at this particular place, average of this particular quantity at this particular place, average of this particular area at this particular place or this particular area. So this is called what? This is called a kernel, and use this particular kernel to multiply all the individual value from here, and then you find out the average. Once again, what do I mean by kernel? You are going to use a 3 by 3 matrix where the values are 1 1 1 1 1 1 1 1, and you are multiplying 1 with 90 1 with 90, and out of the solution you are dividing 1 by 9, and whatever you are going to get you are going to put at this particular place. If you do this, you are going to get this particular thing, and it is going to be a better representation because if you see that what is this particular place, it becomes 80. So now it is not 0, it becomes 80. Similarly, what is 90 over here, it becomes 20 over here. That is more realistic value. I think this is going to be 10 Android. So this is become 10. It's more realistic value as compared to the previous thing. So this operation that we actually are talking about actually makes sense. Okay. However, there is a problem. And yes,
So
is there
would
any
the
question?
image be same after that operation?
Say again. Sorry.
So would the image be same after that operation convolution?
No. So that actually I wanted to focus over here. Let's assume that this is the image that you have, and on that image, if you apply a box filter means 111. That the filter just I talked about 1 minute back. That 1 by 9. If you apply this particular thing, you are going to get this image. So this is not a good image. This is a good image, but this is not a good image. But why we have applied it? Because you have seen that earlier, if you had not applied it, so these kind of large, huge variations you are actually getting. So here I wanted to just point it out. So here, if you see this, for example, if this is the signal that is given to you, and you wanted to analyze, you may think that looks like that these things are going to be happening. These things are happening over here. Okay, by yourself you can tell. Here you can see that there is a difference. Looks like that there is some noise because this value there. That's why these values are very below the original value. So to cater this particular problem, we have actually talked that you can apply a kernel over here, and the kernel can find out the summation and smoothen this particular thing. So it has a smoothing effect, and by this having the smoothing effect, you can tell that these kind of things are there. So looks like that it is a real signal. So we have seen that here, that we have also seen the justification that how it actually works, and here we have seen that okay, no, if you apply these things, you are going to get a blurry kind of image. That is also possible. Another method could be that, as I told you, that when we told you that when to the single line you are going to apply all the values as a one and going to put the average at this particular place, it would be better that if you put more importance to what is the value at that particular place. So sometimes it may be nice that if you can apply some kind of a Gaussian curve over here, because most of the real phenomena are the Gaussian phenomena only. So you can apply a Gaussian over there. So if you want to find out what is the weight over here, so you can apply the Gaussian formula, where you can say that using some kind of parameter you can define that what is the sigma square, what and based on that you can define the formula of a Gaussian, and using this kind of Gaussian equation you could come up that what is the value of the kernels, and then you can apply on the same kind of image, same kind of operation you can again do. So what I wanted to tell that this is the box filtering, and this is where where you can see that this value is higher as compared to this side by thing. So this is a Gaussian kernel. Similarly, this is a bigger Gaussian kernel. This is Gaussian kernel of 3 cross 3. This is of 5 cross 5, and similarly of the different size you can apply. Once again, uh, this was the image that we have seen, that if you apply the box filtering on this, you get this image. That is a bad image. But if you apply this kernel, you apply this kernel on this image, you get this thing. Is it a better image? Right now we are not sure about that, but this is called the Gaussian filtering, and definitely it is better than what? Better than the box filtering. Make sense or not? Yes or no? Right now try to understand that what do I mean by filtering? What do I mean by filtering? So I have a kernel. Somehow I have created this, and we have seen that one method could be all the values 1 divided by 1 upon r k square, or another could be that you apply the Gaussian kind of thing, you find out the summation, divide 1 by that number. Using these things are called kernel. Everybody understand that what is kernel? Can you say yes or no? I apply, what do I mean by applying the kernel on an image? If I put the kernel over here, term by term, I'm going to multiply and find out the exact value. This value I'm going to put at this particular location. So from this image, I got this image. If I apply this one, I get from this image to I get this image. Filtering is a very interesting has a very interesting property. For example, if I create a filter with these kind of values, oh my god, what do I mean by this? So let's assume that I have a this particular array. In array, I am going to put the values with respect to this particular part. What is this? You cannot tell anything, but I have actually taken this particular image from this particular website. So here is a very interesting image you may have seen earlier. So what happens that if I put this particular thing into this if I make the filter of this particular all the values which are there into this small patch, and then if I run this particular patch from this place to the air and top to bottom, so the place where the maximum value I am going to obtain is the place where this particular filter is this particular object is. Okay, so by this you can do a searching also, you can find out that what is over there. Okay, These things can have very nice representation into the signal domain also. You know that into the signal domain, you sometimes you can always say that all the functions, all the things can be represented as a summation of frequencies, and then if you have, for example, G and H, where H is the filter, G is the image. On this, if you multiply, find out the Fourier, is equivalent to finding out the Fourier of G and then Fourier of H, and then their multiplication. What does it mean? What is the meaning of this multiplication? In the Fourier transform domain, I told you that I'm not going to go into the mathematical detail, but actually into the Fourier transform domain, what happens? The time domain signal converts to frequency domain. So this is the signal, and F from the H, this is the another signal. So what happens that you can do the multiplication to the Fourier domain, and then if you apply a inverse on this, then you can find out the original signal. What do I mean by this? That sometime you can do some kind of regularization into the hidden space, and by this you can find out the better representation of the same thing. Okay, this is an image. FFT is going to be this. This is the kernel. FFT of going to be this. You can very effectively multiply over here, find out something like this. Inverse transform gives you this. What is this? You can see that looks like that the places where there is a horizontal images, horizontal lines, they are actually highlighted. So you can find out the salient features using applying these kind of filters. So these filter actually serves to find out different kind of salient features. One more operation that is very needed sometimes is called the sampling. And what is the sampling? For example, this is a big image of the zebra, and I wanted to get the small image. So how can you suggest me to get a small image? You can tell that, sir, every alternate pixel you pick, you drop this particular pixel and you take the next one. So if you drop one by one pixel, you are going to get this small image. Is it a good idea? Yes or no? Once again, my question is this, that if you have a big image and you want to create a smaller image out of that, can you do this? Yes or no? Yeah, why and yes. Yes, you can do it. It's a good thing. But however, there are some problems, and this problem is called the aliasing problem, and that this is not a new to you. You have seen this, for example, funny strip on the shirts and wagon wheels rolling into the wrong way into the movies. You may have seen this. So let me give an example. So let's assume that this is what the signal is. Let's assume that this is what the signal is, and you are actually dropping these particular lines. So what happens that you are sampling these things, so you get this particular point, 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 and you get some this particular point. If you want to construct this signal, looks like that the signal is this, you get this signal, and if you compare this signal and this signal, you can see that they are actually not the same function. So this function is totally different function as the original one. So this problem is called the aliasing problem, and this can appear when actually you do these kind of things. Again, very interesting problem for you. Can you tell me that what is inside this particular image? Who is there? Can you write the name? Can anybody write the name? Who is he? Einstein. Why you are not looking closely? Who is she? Marilyn Monroe. Have you seen this image? Marilyn Monroe. Once again, can you see this? She is Marilyn Monroe. My God, what is happening over here? Let me tell you what is happening over here. So can you tell me that what is written on the screen? Everybody, please write what is written on the screen. Please type. Please type. What is written on the screen? 0. Please type. What is written on the screen? What is written on the screen? What is written on the screen? It is 0. I am writing 0. I am writing 0. I am writing 0. What is written on the screen? Can you write what is written on the screen? What is written on the screen? 0. What is written on the screen? How many of you can see the 0? This is happening because you are seeing these things on the different scale. So that is a very important thing, that when you see the things from the different scale, you are going to focus on the different aspect of the image. So when you are seeing the image from the very far, you are seeing some aspect where there is an image that is of the Einstein, but when you are looking from the very closer, you are going to see the different aspect where Marilyn Monroe is there. So same kind of things is actually being shown over here also, where actually uh, we can say that the frequency component, okay, high frequency component and low frequency component, we have actually mixed these high and low frequency component in single image. Same thing is over here. So these ladies are happy or sad? Can anybody tell they are happy or sad? Hmm? Are they happy or sad? These ladies, they are happy. Are they happy? They are happy. Okay, all of them are happy. But if you see closely, they are not happy. So this is happening because we have actually mixed the low and high frequency component into the same image. What is the high frequency component? Things which are very much changing. Low frequency component which are not changing. So if they are not changing, but you see from very high distance, they keep changing and therefore they become slow details. Look, actually what happened, the high frequency components are actually details and low frequency components are what? They are the salient properties of the thing. For example, here is a text. This text you can read from the distance. You may be reading this, but you cannot read this. Okay, but if you come closer to this, then only you can read. Okay, if you come closer, then you can read, because other things which has been added, they actually go away when you see from the very near. Can you see this? Again, these are the hybrid images. Okay, let me tell you something, that filtering once again. So this is an image. If I multiply with this filter, what I'm going to get? Same thing. Now I need your attention. Okay, if this is an image, I multiply with this thing where there is a 1. So there is a 1 here, means what? This, whatever is this place comes to this particular place. So if this is the original image, you get this particular kind of image where here nothing is there. It is just shifted. It is 1 point shifted image. Yes or no? Yes or no? Okay. Let me give you something more. So this is an image. This is the original image. You multiply 1 by 9, you get this image. This is a blurred thing. Okay. Okay. This is the original image. This is the original image. If you multiply this image with the 2, means all these values are actually going to be increased, and then you subtract by this particular part, which are actually that 1 by 9 of this particular part. What you are going to get? You are going to get this image. So if you compare this image and this image, do you see any advantage? This is more sharper image. Okay, we are started doing something. So on this image, if you apply this operation, that you multiply every pixel by 2 and you subtract the blurred version, you are going to get this image. This is an enhancement. Can you see? Can everybody see that there is an enhancement in this image? Yes or no? What is happening over here is actually I have actually applied 111, and into the same way I have applied 111, I can put the Gaussian over here also. This parameter could be Gaussian also. So let's assume that I'm going to put the Gaussian of the different size. So let's assume that I have an image where there is an owl, and if I put a Gaussian with a 1 pixel, I get this image. Gaussian with a 2 pixel, I get this image. Gaussian with a 10 pixel, I get this thing. Gaussian with a 30 pixel, I get this thing. Hey, try to understand what I wanted to tell. If I apply, once again, very seriously, see this, what I'm going to tell, that if you apply something of the 30 pixel, can you see anything over here? Yes or no? Can you see anything? No. The answer is actually that you can see something. Let me tell you what you can see. You can see, 1 minute, let me close. Okay, here you can see only one thing, this particular thing. Looks like that there is something. Yes or no? You cannot see that what is here and here, but you can see, looks like that there is something here, there is something here. This thing you can make sense. Yes or no? So when I actually put something of the some kernel and I multiply into the image, actually I wanted to see something of this particular size. Only those things are going to survive, other things are going to last. So here you can see something looks like here and here, means like there is something of the 30 pixel is here, something above the 30 pixel is here. 10 pixel, something greater than 10 pixel is here and here. Here you can see that you can see that this particular thing, maybe it is less than the 30 pixels. Still till 10 pixel it was, I think, it's not surviving. So you can see that if small things actually get lost. The size of kernel actually tells, very important thing I'm telling, that what is the size of the item for which actually you are looking. If this kernel is higher, then you try to understand, you only focus on that particular part. So you apply this kernel and you determine that looks like that 30 pixel item is there, and you go into your original image and you cut this particular part and tell me that looks like that something up 30 pixel is here. Understand? So what is the size of the, what is the meaning of this thing? That what is the size of thing that which you actually wanted to understand? Let me give you another example, very interesting example. So this is an image. I am going to, and this is the image. Okay, once again, this is very interesting example. This is an image, and this is another image where it has been smoothened by 5 by 5. What does I mean by this? That 5 by 5 5 by 5 smoothing curler has been, and where 1 divided by 1.25. This is going to be applied on this image, and I get this image. Everybody is clear on that? I get this thing. And if I subtract this image from this image, what I get? I get this image. Can you see what is there? This is called detail. Okay, this is called the detail. So if I use this particular image and multiply by alpha time and add into the original image, what I'm going to get? I'm going to get this image. What I have done? I have added the detail to the image. So that's why if you compare these two images, just compare these two images. Which two images? The first image is this, second image is this. You can see that this image is better because I have added more details to this particular image. Very interesting idea. Any questions on that? A smooth image is subtracted from the original image, and by this you find out that what is the detail that you have. I have applied by 5 by 5 thing. So what happens that if I applied by 5 by 5 thing, so anything that is greater than 5 by 5 is here. If I subtracted from original image, so what is, so anything that is actually bigger than 5 by 5 has actually been destroyed. So what has remained? The things which are actually less than 5 by 5. Those things are a final detail. I have added those final detail by multiplying with the alpha to the original image over here. Original image applied the, added this particular part, and that's why the image become better. Okay. So this particular operation is called the sharpening. Very interesting operation. That this is how you do the sharpening to the images. Now let us discuss one final part to this particular session, and that is about the edge detection. What is the edge detection? So for example, this is an image and you want to find out that where are the edges. So where is the edges? All these things are actually edges. You want to find out that where is the edges, where are the lines. You want to find out where is the line. Okay, you want to highlight that where are the lines. So to find out the lines, you can apply a sx and sy, two kernels. One kernel I am going to call the sx, another sy. That into the x direction, what is the gradient? Sx. Y direction, what is the gradient? So how do you find out gradient? If you want to find out the gradient, you see that what is the value onto the next value and what is the value over here. You take the difference of these quantity. So if you multiply with this, for example, this is what it is, 1 minus 1. So whatever value into the image, for example, on this any pixel you are, if you want to find out what value should be here, so if you multiply this particular kernel, so the nature of this particular kernel is this, that 1 means whatever value here minus this particular value. So this difference is going to be here. Similarly, what is here and what is here, the 2 multiplied by difference is here, and difference between these two quantities multiply 1 by 8, and then you are going to put at this particular place. By this you get that what is the gradient to this x direction. Similarly for sy, find out that what is the up and what is below, the difference between these two quantities, and you find out that what is the difference between these two things. By this you find out the, because two values you are going to get, you can find out that what is the magnitude of this particular gradient by saying that under root of sx square plus sy square. You can also find out what is the direction, that is the tan inverse sy upon sx, what the direction of that particular is. And if this strength is actually greater than some value, you apply some threshold and you say that if the value is greater than this particular some threshold maybe 0.5, if the value is greater than 0.5, you put the pixel, that particular pixel as on. Once again, once again, what I'm telling, I am telling this, that on this image, you are applying a filter. Which filter? This particular filter. This particular filter. and applying this filter you get this particular value. Okay, what is this particular value? That what is the sx in the x direction, what is the what is the value, what is the strength? If the strength is higher, you can see the higher value, otherwise lower value. Similarly, what is the strength in y direction, sy? Then you combine these two things to find out this particular quantity. If this particular quantity is greater than some threshold that you decide, then you say that those pixels are actually on, other pixels are actually off. If you do this and you create, you highlight those pixels which are actually going to be on, you get the pixel something like this. And this particular method is called, here you can see that with respect to this image, if you compare this image and this image, you can see that only the pixels where there is a edge, they are actually highlighted. Make sense? So this is called the edge detection. So that's